All right, so I wanted to make a second part to this lecture and just kind of follow up on maybe part of the slide that we didn't talk about, where we go into types of energy and the conservation of energy formula. Um, as for types of energy, I'm going to kind of probably spill over a little bit here onto this area down here. And so let's start by just talking about the different types with kinetic energy. So I'm just going to go ahead and label them. This is moving energy, and if you don't have enough space, then obviously get a separate sheet of paper. So anytime an object is moving, it has moving energy, and the formula here is Ke equals 1/2 mv squared, where m is the mass, units are kilograms, v is in meters per second, or velocity is in meters per second, and kinetic energy is in joules. So there's our first type. Our second type here is potential energy, gravitational, which I'm going to put a little g under that. Let me go ahead and so let's write that down. And that might be kind of hard to see, but this is gravitational. Another symbol for this would be UG, where U stands for potential energy. And formula here for PEG or UG is MGH. And so this is kind of energy of position, is maybe a way to think of this. Let's go ahead and maybe write that maybe over here is probably a good place. So when an object is in the gravitational field on Earth, it has potential energy because of that. So this is due to the fact due to the object being in the Earth's gravitational field. And this is kind of tricky, right? Because if you think about it, if an object was infinitely far away from the Earth, it would have zero potential energy. But a lot of times with the energy of position, which you guys are already kind of familiar with, is that the zero potential energy occurs when you're on the ground. And I guess if you were higher up in the air, right, you would have more potential energy. So it looks like this, right? Like if I drew a picture of a person on the ground, that when they are standing here, their potential energy gravitational is 0 joules. And then if there was or if they say jumped up in the air, then their potential energy would be based on whatever this whatever this new height is, right? And so we're going to see height as part of the formula that gives an object potential energy. And now UG would equal to some number. Now, the reason I say this is tricky is that if you think about it, if you are at a distance from the Earth, right, where say R is equal to infinity, then your potential energy, because you're so far away from the Earth's gravitational field, your UG should actually equal 0 joules. So how can this be the case that your UG is 0 joules right here, right, on the ground, and then it's some positive number right here? This would be a positive number, maybe like positive 1,000. I don't know, I'm just making something up. And then at the same time, if you are infinitely far away, we go back to the potential energy being 0 joules. So this is kind of a confusing topic and something that we'll get into more in the future. But just, I guess, if you want to think about it this way, that this formula, and maybe this will explain what I just said, is that this formula is only valid on the Earth's surface. That if you go off into outer space, you need a new potential energy gravitational formula. And that's exactly how we fix that problem that I just mentioned. All right, so coming back to this, let's see. So this is the mass of the object, and this is in kg. This is the gravitational field, or baby g. It's 9.81 meters per second squared, and that is the Earth's gravitational, gravitational field. I don't know why that doesn't look right, like I spelled it wrong, but I think that's good. And then this is the height in meters. All right, so we have this nice formula, and once again, use whatever symbol you want. If you want to use UG, go right ahead. Feels a little more sophisticated than PEG, but you know, do whatever you like, whatever's easiest. All right, so let's go ahead and go to another type of form, or another type of energy here, and that is potential energy of a spring. So I'm gonna probably have to box this off somehow. Ooh, I don't like how much room I have there. I'm gonna come down here. All right, so we have PE of a spring, and yeah, I guess we can write it that way. I was gonna say we could write it as PE spring. You might write it as PE elastic. And you might write it as US for potential energy of a spring, right? So I'll go with that one right now. So potential energy of a spring is equal to, it's very similar to or it looks similar to the kinetic energy formula, actually. It's 1/2 kx squared. And one more thing I forgot to mention is that your units on UG is joules, right? For any type of energy, our SI unit or our unit is going to be joules. All right, so coming back down here, we have obviously potential energy of a spring is going to be in joules. On the other side, we have K, which is called the spring constant. It is a number that tells us how strong the spring is. And a larger K means a strong spring. Sorry if that's hard to read. Let me put another page in here to kind of break this up a little bit. All right, there we go. Looks like I lost a little bit of my writing there. All right, so a larger, how strong the spring is. Did I lose more than that? Strong the spring is a larger K means a strong spring. Okay. So so we have that. And then finally we have X, which is the distance. It's not the length of the spring. It is the distance the spring is stretched or compressed from equilibrium. All right, and that's going to be in meters. What's the units on K? The units on K are newtons per meter. Okay, so there you have it there. All right, so getting back to what X means, if you had a spring that, say, was attached to a surface, maybe it's attached to this wall here, and it's just sitting here, right? And this length right here would be equilibrium, right? It's just sitting there at equilibrium, and then you were to take an object and you were to then attach it to the spring, and you were to stretch it to say here, this mass. And what that would mean is that this distance from equilibrium, which is right there, right? So equilibrium is still right here. Maybe if I use a different color, that's easier to see. So this right here, this length, or this point, this position is the equilibrium position. And so what I'm saying then is that distance right there, because you can think of the mass as starting right there, is that this distance that it was stretched or compressed, which down here is in red, would be x. And and that gives us our potential energy of the spring for the object. All right, pretty good. Okay, so let's go ahead and look at other types. I think there was a couple more here, U internal and delta E thermal. Both of these are, I can probably write it right here. Looks like I got some room. Both of these are the same thing. So it's the same as U internal. And it is the heat shared between two surfaces. And that's why you see the delta here. A lot of times we don't know what where this energy is, right? Like which surface has it. We just say it's somewhere in between the two surfaces. And we'll come back to this later. Formula here for delta E thermal or U internal is equal to the forced friction times the distance. All right. Good. Let's go ahead and and that'd be force friction kinetic, by the way. All right. Let's look at conservation of energy. So I'm going to go ahead and add one more page here. Just get a little more room. All right. So conservation of energy is very simple. At the start, right, it is just energy initial is equal to energy final. In some physics textbooks, you might see the final written on the left side and the initial written on the right side, and you're free to write it like that if you like. I tend to write it this way because a lot of the students are just starting off with this concept, and it just kind of helps with that. Another way you might see it written besides like this is you might see it written as mi equals mf. And this is mechanical energy. What is mechanical energy? Mechanical energy is Ke plus Pe. And that could be potential energy, gravitational, or potential energy of a spring. Okay. Good. All right. So another way this sometimes can come into play is that when we write, say, energy initial or energy final. Let me go ahead. Stupid calendar event is in my way. All right. Yeah, so. All right, so let's go ahead and split this right here. All right, and I'm going to go ahead and say that EI and EF are both equal to the total energy. So meaning that when you have the initial energy, that is also the total amount of energy you have in the system, right? And I just want to point that out because sometimes I like to write this. I like to write E total is equal to, say, PE plus KE. And this is kind of getting at an idea that at its most simplest, right, when you write your energy initial equals energy final, when there's no external forces and you're looking at something maybe like a roller coaster, right? When this happens, you can go ahead and simplify this into and there's no springs on a roller coaster, so you can simplify it into something like this, where you would have PE gravitational plus initial plus KE initial is equal to PE gravitational final plus KE final. And so a lot of times our equation just simply becomes this. And this is pretty good most of the time. But there's sometimes where this gets a little tougher to work with, right? Like maybe you have a spring. Maybe you have internal energy, right? So I just want to point this out, that while this is the form of energy conservation at its simplest, we can see right away that if work is being done, this isn't going to be a good enough equation. So let's look at that. So if you have energy initial is equal to energy final, well, actually, let me write it this way. Let me start here. Let's start with just the definition of work. Work is equal to a change in energy. We know that work then is equal to EF minus EI. And we can see that if we kick EI over to the other side, EI plus work is equal to EF. Hopefully you just see the move there. I just added EI to both sides. Cancel, cancel, just like that. And we can see that we get this equation, or conservation of energy equation, which is a little more complicated, right? Because it deals with the fact that maybe you have an external force that's doing work. And now this is our energy conservation formula. And so energy conservation formula can even look even trickier than this if there's a spring involved as well, right? So this can take the form of, say, something like this, where you would have PE gravitational initial plus KE initial plus PE of a spring initial plus work. Notice that work always goes on the initial side. And then that's the trick to that, is equal. And now you can write the other side of the formula, which I don't know if I have in room, but I think I do. PE gravitational final plus KE final plus PE of a spring final. And there you go, right? And finally, another way this might show up is with delta U internal or delta E thermal. And if either of those do show up, you would see something like this. You would see delta E thermal on this side. And this could also, or U internal. Finally, realize that this is an external, this is done by an external force. So when you see this, and then also realize that sometimes you're going to have delta E thermal, and if you do, you won't have work being done by that force. And I'll talk about that in another lecture. All right, so there you go. Conservation of energy can be written a lot of different ways, but realizing that I think at its simplest, it's EI equals EF or MEI equals MEF, just like this here. If you don't have a spring and there's no external forces, then you can just write PE grav plus KE initial equals PE grav final plus KE final. And then work always shows up on the initial side. And you can even take it a step further if you have a spring and expand it out a little bit. And if delta E thermal or U internal shows up, that's going to be always on the final side. And I'll get into that later, why that's the case. All right, that's it. Have a good day.